video session on operating modes and working of MOSFET in the CMOS VLSI design. I am Professor Srishel Prakash Swami from Walchand Institute of Technology, Solapur. These are the learning outcomes. At the end of this session, the students will be able to understand the operating modes of MOSFET and understand the operating regions of MOSFET. The contents in the operating modes of MOSFET, we are discussing the accumulation mode, depletion mode and inversion mode. In the operating regions of MOSFET, under the working of MOSFET, we are discussing on the cutoff region, the linear region and saturation region. So this MOS layers and the symbols we discussed in the last session. So in the MOS, the P type and N type MOS devices, there are the three different terminals known as the gate terminal, source terminal and the drain terminal. So in the MOS transistors, the any one symbol which is shown here in this figure we can use for designing of the any combinational circuit and sequential circuit and etc. So we can here this diagram, if we are referring, so there is a channel exists between the drain and source when we are applying a sufficient voltage at the gate terminal. Now the width of the channel is controlled by the voltage on an electrode which is called as gate, means this width between channel of width between the source terminal and drain terminal is totally controlled by applying the gate voltage which is we can say that the applied voltage which is known as the VGS, and it is the channel is located between the source and drain. It is insulated from the channel near an extremely thin layer of metal oxide. Now there are the three operating modes of the MOSFET: accumulation mode, depletion mode and inversion mode. Now the first we can start the operating modes. In the first step is accumulation mode. So here if you are observing this diagram, then we can say that this is here the p type body is there as the body part, means what, this is what the NMOS. So for this NMOS transistor, when a sufficient voltage is applied which is known as VG applied at the gate terminal or between gate and source, when the VGS is applied and here the VGS is shown as which is less than 0, okay, means negative voltage when we are applying at the gate terminal of the NMOS, then we can say that there is negative charge on the gate. When the VG voltage less than 0 is applied at the gate terminal for the NMOS, then negative charge will appear on the gate which is shown here, okay. So here the negative charges are accumulating nearby the silicon dioxide insulating layer. So the mobile positively charged holes are attracted, means the holes which are nearer to the silicon dioxide insulating region, they will trying to attract towards that region. So this is called as what, accumulation mode, means the electrons are trying to accumulate nearby the gate. So second mode of operation is what, the depletion mode, means here for same NMOS, now the voltage VGS is applied but it is now greater than 0, and that is what, positive voltage, but less than threshold voltage. So threshold voltage is denoted as VT, means it is greater than 0 but less than threshold voltage. Now what is the threshold voltage? The threshold voltage means the sufficient voltage or minimum voltage applied at the gate terminal of NMOS so that NMOS can be on. So in this figure the gate voltage is applied less than threshold voltage but greater than 0 here. So here when we are applying such a voltage to the gate, then it results in some positive charge on the gate, means the positive charge will accumulate nearby the silicon dioxide layer. Then the holes in the body which is in the p type body, they are starting to repel from the region directly beneath the gate. So this will result in what, the depletion region forming below the gate. So here the depletion region is formed just below the insulating layer, okay, which region known as the depletion region. Now next, the third one, the inversion mode. So in the inversion mode, now the sufficiently the large voltage is applied, or the voltage VGS which is greater than threshold voltage is applied at the gate terminal or between gate and source terminal. So the threshold voltage VT depends on the number of dopants in the body and the thickness TOX of the oxide. Means what should be the threshold voltage exactly value, that depends on two parameters of NMOS, that is what, the number of dopants in the body and the thickness of the silicon dioxide layer, that is measured as TOX. So here as shown in the figure, the VG is greater than VT is applied at the gate terminal, which is greater than threshold voltage. We can say that it will attract the more positive charge to the gate, means it will try to attract the more positive charge towards the gate. The holes are repelled further from the p-type body and some free electrons in the body are attracted to the region beneath the gate. So this conductive layer of the electrons in the p-type body is called as what, inversion layer. Means in the p-type body, before applying any voltage, only positive charge were, but when we are applying the gate voltage more than threshold voltage, the negative charges will accumulate in the p-type body. This will forms what, the inversion layer. So we can say that there is inversion of channel in the p-type body. So these are the we discussed up to the operating modes of the NMOS and PMOS transistor. Now we can discuss the operating regions of NMOS transistor. There are the three regions already we discussed: cutoff region, linear region and saturation region. Now as shown in figure here, this is what NMOS transistor. So gate to source voltage applied is 0 and the between drain to source, that is known as VGD. So here as shown in figure, the transistor consisting of the MOS stack between two n-type regions called source and drain. In this figure, the gate to source voltage VGS, which is less than the threshold voltage. Okay, so it is less than threshold voltage means nearby 0 is applied. So when the transistor for the NMOS transistor, when we are applying the applied voltage less than the threshold voltage, then transistor NMOS will be in the cutoff region. So here the source and drain have free electrons, the body has free holes but no free electrons. Suppose the source is grounded, the junctions between body and source or drain are zero bias or reverse bias, so little or no current flows. So we can say that the transistor NMOS is off. So this type of mode of operation is called as what, cutoff region. In the cutoff region, the VGS is less than VT or nearby 0, we can say that, and the current flowing between drain and source is 0 because transistor is in off condition. So second region is linear region. So in the linear region, VGS is increased above the VT. So in this figure, the gate voltage is greater than threshold voltage is applied at the between gate and source. Now an inversion region of electrons, which is known as majority carriers, called the channel, connects the source and drain. Means whenever the VGS is greater than VT is applied between gate and source, then there is a formation of the channel between drain and source, so creating a conductive path and turning a transistor on. So in the linear region, the number of carriers and conductivity increases with the gate voltage. The potential difference between drain and source is given by VDS. VDS means VGS minus VGD. If VDS is 0, means drain to source voltage is 0, then there is no electrical field tending to push current from the drain to source. So in the linear region, the minimum condition is what, the VGS should be greater than VT, but the gate to source voltage is also greater. So when a small positive voltage VDS is applied, the drain current IDS flows through channel from the drain to source. This mode of operation is called as linear, which is acts as a resistive. The current increases with both drain voltage and gate voltage. Means as VDS you are increasing, the current IDS also increasing. So that region is called as linear region. So in the linear region, if VDS becomes sufficiently large, then VGD becomes less than VT. The channel is no longer inverted near the drain and becomes pinched off. Means channel length is going to reduce here. So next, last region of operation is saturation. In the saturation region, the VGS is obviously the greater than threshold voltage, but the current IDS will not depends upon the value of VDS because the channel is already pinched off. So in the saturation region, the conduction is still brought about the drift of electrons under the influence of positive drain voltage. As electrons reach the end of channel, they are injected into the depletion region near the drain and accelerated towards the drain. So above this drain voltage, the current IDS is controlled only by the gate voltage and ceases to be influenced by the drain. So this mode is called as what? The saturation mode. So in the saturation mode, the important thing is what? The IDS independent of VDS. So summary. So for the NMOS transistor, the NMOS transistor has 3 modes of operation. If VGS, that is gate to source voltage, is less than VT, the transistor is in cutoff, that is it shows the off state. If VGS is increasing greater than VT, the transistor turns on, and simultaneously if VDS is small, the transistor acts as a linear resistor in which the current IDS is directly proportional to applied voltage VDS. So if VGS is greater than VT but VDS also increase or large, the transistor acts as a current source in which the current flow become totally independent of VDS. That is what saturation region. Now this is summary for PMOS transistor. The PMOS transistor has 3 modes of operation. If VGS is greater than VT, the transistor is in cutoff, exactly opposite to the NMOS. If VGS is less than VT or less than threshold voltage, the transistor turns on. If VDS is small, the transistor acts as a linear resistor in which the current flow IDS is proportional to VDS. If VGS is keeping greater than less than VT and VDS is increasing or keeping sufficiently large, the transistor acts as a current source in which the current flow becomes totally independent of VDS. So this is what the saturation region. So these are the references: CMOS VLSI designed by Neil H. West, David Harris, by the Pearson Education, and second one is the principle of CMOS VLSI design by Neil West and Kamran Ishragan by the Pearson Education. Thank you.